All right, we're going to now introduce the subject of observers. We will look more closely at this in the following lecture. So we've talked a little bit about state feedback. In general, only a small combination of the states are measured. So if you're given a state model, generally speaking, you're only measuring a small combination of the states. Sometimes it is either not cost effective or it's actually impossible to measure all the states. You can't actually get a sensor into some places. We also might wish for some filtering of the states that are measured. So the question is, can we use estimates of the states instead of the actual states for feedback? So that's an important question. Well, so in looking at this question of observers, we want to estimate the state x. So given the system, x dot is equal to ax plus bu, y is equal to cx plus du, with unknown initial condition, can we test whether the system is observable? So we know that we can test whether the system is observable or not, but what does that buy us? Well, when we looked at the subject of observers, we saw that observability could help us determine the unknown initial condition. So we had that, but in general we would wish to detect not only the initial condition but all the values of the state. So not just the value at time 0, but all the values of the state. And so the question is, can we estimate the values of x of t even if we don't know the initial condition of x of t? Now, since we know that x of t follows a certain behavior, we can mimic that behavior. So here is the first try at an observer. So x hat is the estimate of x. So x hat dot, we can just have it satisfy the same differential algebraic equations. Again, because we don't know the initial condition on x, we can just assume x0 is equal to 0. We need to choose something, so that is as reasonable a choice as anything. So this system will exactly follow the dynamics of the original system. Again, we choose the 0 initial conditions since we don't know what else to do. We do have the actual value of u because we're going to apply that, and so we know that. So we don't know the initial condition, but we do know the output. And so important question is, will this work as an estimator? So we're basically mimicking the system. Will this give us a good estimate? And so an important other question is, how can we tell if this is giving us a good estimate? How can we tell? How do we know if this is actually even giving us a good estimate? Well, now we're going to look at something called the observation error, the difference between x and x hat. So if this estimation error goes to 0, then we know that if it's equal to 0, then we know we have a good estimate. That is, the estimate is equal to the original state, and that's good. So because of the fact that we have dynamical systems, we can actually look at the error dynamics. So we look at the derivative of the error with respect to time, which is the derivative of x with respect to time and derivative of x hat with respect to time. X is equal to ax plus bu, x hat is equal to ax hat, x hat dot is equal to ax hat plus bu. The bu terms cancel, and we're left with a times x minus x hat, or a times the estimate. The error. So the solution to that differential equation is given by this expression. And if A is Hurwitz, that is, if it has all its eigenvalues in the left half plane, then this estimate goes to 0 as time goes to infinity. That's not bad. We could work with that. So that is, the estimate improves, which is good. However, if A is not Hurwitz, then the error doesn't go to 0. And in fact, the error might even blow up. So basically, mimicking the system behavior is not enough to have a good estimator or a good observer. All right, so we're going to do a second try. Basically, we're going to mimic the behavior, but we're going to have a correction term. So all of this mimics the behavior, and then we add this correction term, some constant times y minus y hat. If this is exactly 0, then we recover the original dynamics of the system. Okay, and again, we assume 0 initial condition because we don't know what else to choose. So if you look in the original form, the observer, it required the input of the system to form the estimate, but it didn't use the output of the system. Now, in this corrected form, we now are using not only the input to the system, but also the output of the system. We're basically using all available real-time information to generate the estimate. So here, this script O refers to our observer, which gives us the output. So now this shows that we're using all the information available to us, and that can work. So now we check the error dynamics to see how it works. So again, x dot minus x hat dot, here's x dot, here's x hat dot. We can go through and keep in mind that y is equal to cx plus du. Y hat is equal to cx hat plus du. So the bu terms cancel here, the du terms cancel here, and when we simplify this down, we get a minus LC times the estimate. So what this tells us now is that the stability of the error dynamics depends upon a minus LC instead of just a. And we have already seen that if the pair AC is observable, it will be observable if and only if the roots, the eigenvalues of this matrix are arbitrarily assignable by appropriate choice of L. That is, we can put the roots of this polynomial anywhere we want. We've also seen that if AC is observable and we have a single output system, we can use a variation of Ackermann's formula to compute the observer gain. So alpha O is the desired polynomial of A minus LC, and we evaluate that at A. We use the inverse of the observability matrix, and then we have this matrix. Again, we have the observability matrix and the desired characteristic polynomial alpha O of S. So we can actually get an L that will place the eigenvalues of A minus LC anywhere that is specified by alpha O, which we can pick. So the observer that we've just defined is called a full order observer because the observer is of the same order as the plant. This might be inefficient to implement if the plant is of high order. But this is the observer. Stay tuned now for practice problems.